almost impossible to compare to cover all the 100 instructions in just one lecture. So what we will do is we will start with the addressing modes. We will cover some of the instruction set, maybe 50%, and then after that, whatever will remain, we will definitely cover that in the laboratory session. Or we have already gone through those instructions in the laboratory session, but we will see where they are grouped. I mean, instruction set is grouped into various titles. So we will quickly see where they are grouped, and we have already used them in our laboratory, right? So for the sake of completeness, we are going to start with addressing modes today. And can somebody quickly tell me what do we mean by addressing modes? Because we have covered this topic in 8085 also. What do you mean by addressing modes of any microprocessor? Anyone with some idea? So only 32 people are there. Okay. So by addressing modes, what we mean is, suppose we see any command. If you see any command in 8086 or 8085, obviously that command would be doing data manipulation for most of the times, which do not do any data manipulation. So if the commands are doing data manipulation, then where are we bringing the address of that data from? The data which is being manipulated or which is being transferred, where are we getting the address of that data from? That's what we mean by addressing modes, right? So here in 8086, the addressing modes, they are divided into 7 different parts. They have 7 different titles, and we will discuss each and every addressing mode with a simple example. And probably we have already learned all these commands already, but just to see what addressing mode they have got, I have got this table, and let us start them and let us study them one by one. So the first example that we have is move bx comma cx. This command is very simple command, and we have seen this multiple number of times. The purpose of this command is simply to move the data from cx register into bx register, right? So move destination comma source. This destination and source could be either they could be either two registers of same number of bits. For example, 16-bit registers are there and 8-bit registers are there. Then it could be one of the memory locations in one registers. That is also possible, but both of them cannot be memory locations because microprocessor cannot be bypassed, right? So both of them cannot be memory locations, and these two registers are already there, right? So the purpose is just to copy the data. The data from CX register will be copied to the BX register. And to be able to see which addressing mode this move BX comma CX should belong to, the data which we are trying to manipulate, its address should be found out, right? So here you see that the data which we are trying to manipulate, it is already kept in CX register, and it is getting copied to BX register, right? So it is already kept in CX register. So the address where this data is being kept, since registers do not have addresses inside 8086, that is why this addressing mode is called as register addressing mode, right? Register addressing mode. I mean, the data on which you want to operate, it is kept in some of the registers. So that is why this is register addressing mode. After that, let us take the next example. In this next example, you have this command move bx, comma 1234 in hexadecimal. Now, this command will simply move a data of 1234 in hexadecimal inside the BX register, right? So now the data which we are going to operate on is 1234, and this 1234, it is a part of the instruction only, right? We are not trying to read it from somewhere inside the external memory or maybe from the peripheral. So it is not the case. This data is directly available or immediately available in the command itself. This is a 16-bit data, right? So that is why this mode is called as immediate addressing mode. This is called as immediate addressing mode. the data on which we want to operate, it is a part of the command itself, right? So that is why it is called as immediate addressing mode. Now, after that, we have got this command move cx comma in brackets 1234h. So the meaning of this in brackets 1234h is whatever is kept at this particular address location in the externally interfaced memory in an appropriate segment, that data will be moved to CX register, right? So, I mean, it, this 1234 has to be an offset address. It cannot be an absolute address, absolute 20-bit address. It has to be an offset address. And assuming that we are dealing with the data segment only, so inside that data segment, we have got 64 kilobytes of locations, and the 1234 offset in that, the 1234 offset from the beginning of the data segment at that particular location in the externally interfaced memory, whatever 2-byte data is kept, it will be moved into this CX register in the little endian form, because this is a 16-bit register. So the data that we are going to move will be of 2 bytes. 2 memory locations will be copied into the CX register. And how they will be copied? They will be copied in the little endian fashion. That is higher order byte to the higher order address and lower order byte to the lower order address. So in this case, 1234H is the address of the data, which we want to manipulate. So where is that data kept? The data is actually kept in the externally interfaced memory. And how do we obtain the address of that? So the address is directly available inside the command. So that is why we call this as direct addressing mode, because the address is directly available in the command. Now, the point of difference here between the immediate addressing and the direct addressing is, in the immediate addressing mode, the data itself was available directly. However, in the direct addressing mode, the address of the data is directly available, right? So sometimes these two might sound confusing, that immediate addressing mode is there and direct addressing mode is there. So is the data, or is it the data, or is it the address that is immediately or directly available? So immediate terminology, it is used for data, and direct terminology, it is used for your addresses, right? So after that, we have got this command move cx and in bracket si. This command is similar to the previous command that we have studied in the direct addressing mode. The only difference is, instead of keeping the data, instead of keeping the address into the brackets, this time we have kept the address inside the SI register, and that SI register is being used for accessing that particular memory location, right? So that is why it is called as register indirect addressing. Register indirect addressing, right? Because this register is holding the address of the data which we want to manipulate. That is why it is called as register indirect addressing mode, right? So the only point of difference being in this 3 and 4, that is direct addressing and register indirect addressing, is in the first case the address was directly available inside the command, and in the second case the address is indirectly available in the command. It is kept inside the register. That is why it is called as register indirect addressing mode. Similarly, we have this command move si, and then there is some another offset 0002h, or then we want to move a data of 92 to h. So we discussed these kind of commands where we said that the physical address will be calculated by the address, the base address, of course, which is the address of the data segment which we want to deal with. Then offset will be kept in SI register, and after that offset, again then there is some bias term which is 0002h. So three things will be added: the base address after appending a 0 to it, then the contents of SI register, and the contents which are written inside this bracket. So at that physical address, this 92h data will be moved. So here you see the name of this addressing mode is direct or register relative addressing mode, right? So here you can see you have got a register and you have got a relative address. So SI and 0002. Because of this, we are calling it as register relative addressing mode. Register is there, and then there is a relative offset. So we call it as register relative addressing mode. Similarly, if you look at the base index addressing mode. Here the same thing is getting done, but you are using one of the base registers. We have discussed this. Either you can use a BX or a BP, and together with that you are using the index register. That is why it is called as base then index. So base index addressing mode. So you are trying to copy a data of 93H into the location which is indexed by BX plus SI. That is why it is called as base index addressing mode. And here in the last command, if you see, you have got the same command, but you have got a relative offset also. So it is called as relative base index addressing mode. Relative base index addressing mode. So base is there, index is there, and some relative address is there. So it is called as base index, relative base index addressing mode. Right. So these are the addressing modes, and just by seeing a particular command, you should be able to identify what is their addressing mode. An addressing mode, it simply means that the data on which we want to operate, where do we bring the address of that data from, right? So you should be able to identify which addressing mode a particular instruction which is written it possesses, right? So any doubts in this so far in addressing mode? Any doubts in this addressing mode? Anyone? Okay, so how many of you are still present? Please raise your hands. Okay, so it's only 33 people. Please put down your hands. So after reading the addressing modes, now it is the time for studying the instruction set of 8086, right? So
Sir,
yeah, just tell me.
sir, in register relative addressing, SI and then 0002 is written. It means that after SI plus 2 address is
Yes. We have discussed this earlier also. In these addressing modes, in this command, what happens is, suppose DS register is there. The DS register, it contains 5000 H, right? It contains 5000 H. So what will be the actual base address? It will be 50,000. Is it or is it not?
yes, sir.
Then suppose the content of SI register happens to be 0003H. So for SI you have got 0003 in hexadecimal, right? And this 0002H is already there. So 0002 H is already there. So how do I calculate the actual physical address? I will take a 0 and append after this 5000. So it will become 50,000. So 50,000 plus 0003 plus 0002. So it will become 50,005. So the actual physical address will be 50,005. Is
Okay,
it
sir.
clear? So we have
Yes, sir.
discussed this. We have discussed this while we were discussing indexing in 8086, and this facility is there in 8086 to facilitate some kind of double loops or triple loops if you want to make them. Because you can see here in this base index addressing mode, you have got the same thing inside one base register and one index register. So you can change the contents of BX and SI, and you can iterate over a loop. So for facilitating that, these kind of commands are made, right? Is it clear now?
Yes, sir.
Okay. So now in the instruction set is instruction set. This 8086 it contains about 100 instructions, and those 100 instructions are categorized into one of these 8 categories, right? Into one of these 8 categories, and it is not necessary. It is not necessary that one instruction, if it belongs to the data transfer group, it cannot belong to any other group, right? So broadly speaking, these titles that are given, they are approximate in nature, right? An instruction might belong to looping instructions. It might belong to looping instructions, and it might also belong to suppose this data copy and transfer instructions. So it might happen like that. But broadly speaking, all of these instructions, they have approximate meaning. All of these titles that you see, they have got approximate meanings. And already we have studied some commands from each set. But just for the sake of completion, I am showing you some important commands today from every set possible, and whatever sets will be left, we will be covering them in the laboratories, obviously, because anyway we are going to make many programs, right? So instruction set of 8086, it is divided into 8 parts, out of which the first is data copy or transfer instructions. And this group of instructions, it will have mostly move instructions and its variants. So data copy or transfer instructions are like move instruction and its variants, and some other instructions are also present there, right? So arithmetic and logical instructions. Now this arithmetic and logical instruction set of 8086 is different from 8085 in various senses, right? For example, in 8085 we didn't have a command for multiplication or division, right? We also didn't had any overflow flag because of that. So this instruction set of 8086, the arithmetic and logical instructions are richer. They are rich in nature as compared to 8085. Another example could be, you can do a signed multiplication and unsigned multiplication, right? So that is also there. So there was no care given to the sign of something in 8085, although there was a sign bit in flag register, but that was applicable to calculations. After calculation, a sign bit is set or reset. Here in 8086, you will also be able to do some signed bit calculation, like signed bit multiplication and division, etc. So arithmetic and logical instruction set of 8086 is richer as compared to 8085. And branch instructions, we already know these branch instructions, they will transfer the control from one point of the program to other point of the program. And a good example of branch instruction is jump instruction and its variants. Also, you have call instruction, and in 8086 there are no variants of call instruction. I mean, for example, if you have jump instructions, in jump instructions you will have conditional jump as well as unconditional jump. Unconditional jump is simply jumping from one place to another, whether some condition is satisfied or not. But a conditional jump is the jumping when certain condition in flag registers is satisfied. So that way, for jump instructions, you have two sets. However, in call instructions in 8086, you only have one call instruction, CALL. There is nothing called as call on carry, call on zero, as we had in 8085. So that thing is not here. This call instruction will be able to achieve the purpose of calling a function. So there is nothing called as conditional call. There is only a simple call instruction. So those are all a part of branch instructions. Branch means transferring the control not in a sequential manner. You can just transfer it the way you want. Then there are looping instructions. We said that there are dedicated commands for looping instructions. So they are also divided into conditional part and unconditional part. So like LOOP is the command for looping, and for conditional looping you can have loop on 0, loop on no 0. So loop Z and loop NZ. These commands are there, and they are run based on satisfaction of certain conditions, right? So looping instructions are also there, and the special thing about these looping instructions are to be able to control their iteration parameter, because inside a loop something has to we have to iterate over something. So the counter of the loop, it is maintained in the CX register, because we have seen that if you want to implement loops can be implemented by using branch instructions also. But branch instructions, inside branch instructions, we have to take care of the loop counter by ourselves. However, the difference between branch instructions and loop instructions in terms of jumping, in terms of maintaining the counter, is that loop instructions, they will have a dedicated counter for them. So whatever we will keep in CX register, it will keep on decrementing, and once it reaches 0, the loop will automatically stop. So that way we have got these loop instructions also. For this is valid for unconditional loops, right? For conditional loops, you will have the satisfaction of the condition like loop not zero or loop on zero, etc. for coming out from the loop. So loop instructions, the default register happens to be CX register here. Then there are some machine control instructions. Machine control instructions like halt. Halt instruction is a machine control instruction which will just simply stop the computer, right? So some few machine control instructions are there in 8085. Then there are flag manipulation instructions. One example of flag manipulation instruction is CMC. CMC means complement the carry. We have seen this in 8085 also. So CMC is also there. So flag manipulation instruction, you will be able to modify either individual sensible flag bits, because the entire format of the flag register that we had seen in previous lectures, it is not usable. Some of them are don't cares and some of them are usable bits. So you will be able to modify their bits, or you will be able to modify the upper or the lower byte as a whole. So there are certain flag manipulation instructions also, right? Then shift and rotate instructions. So we have seen in 8085 that RAL and RRC etc. were there, in which the contents which were kept in accumulator, their binary version, if we consider them, that binary version is either rotated in a clockwise or anti-clockwise fashion, depending upon whether we are doing the left shift or the right shift, and it could be done through or without the carry flag. So those similar kind of instructions, shift and rotate instructions, are already there. And the reason for existence of this shift and rotate instructions in any microprocessor is for creating various series. So we will see a working example of that in the laboratory. And then there are certain instructions which are called as string instructions. To be able to deal with string, to be able to copy a chunk of bytes which we call as a string from one place to another, you have got string instructions, right? So these string instructions, they will appear in this data copy group also, arithmetic and logic group also, branch instructions also, because ultimately if you want to copy the data, that data could be string. If you want to do arithmetic operations on two strings, that could also be possible, adding their ASCII values, etc. Right? So string instructions could be a part of any of these set, but we have broadly classified them into one separate category. So we have got these string instructions. So these are 8 different classifications of instruction sets in 8085. So let us now start. Let us now start to study this instruction set, starting from the data copy and transfer instructions. So on the left you can see I have written all the data transfer and copy instructions that you have got. So there are 14 such instructions, some most of which are already known to us. I will only give time to those instructions which we haven't seen up till now. For rest of the instructions, you already know what is being done. So we will just touch them and leave them as is. So the first instruction that we are going to talk about is move destination comma source. We are already aware of this, so I'm not paying any attention to this. You are just trying to copy the data from source to the destination register, and it's a copy command, right? The format is destination comma source. We have used it multiple number of times. Then you have got this command push comma source. Push source. So here the important points which you need to note for a particular command, I have written it here in these form of lines. So source register, source can be a register or a memory, and it operates on a word. So we already know that for stack operations, whether we use push command or pop command, it will be operating on 2 bytes, or it will be operating on 16 bits. This was also true for 8085, despite of the fact that 8085 was a 8-bit microprocessor, right? 8086 is a 16-bit microprocessor, but still the stack will be operating on 2 bytes simultaneously. And to be able to push the data onto stack, you have to keep the data somewhere, and that somewhere is called as source. So what that source could be, that source can be a register of 16 bits or a memory location of 16 bits, I mean 2 consecutive memory locations, and this command operates on words. And how is the data copied? It is again copied in little endian fashion from the source to the stack. Lower order address on the lower order data on the lower order address, and for the higher order address you have higher order data, right? Similarly, the pop command is the reverse command of this push instruction, and here also the source can be a register or a memory, and it also operates on a word. So these push and pop commands, it is also advisable to use equal number of push and pop commands inside a function. If you write a function in 8086, it is advisable to keep push and pop in equal numbers, because if you do more pops than push or more pushes than pops, in that case the return address when the function returns, it might be changed, right? We might not be able to use the correct return address. That is why this push and pop instruction, if you are trying to use them inside a function, then you should be using them in equal numbers, right? Even if it is useful or not, right? Then similar to this push and pop command, you have got this push f and pop f command. What will it do is, it will put the contents of the entire flag register, which is of 16 bits or 2 bytes, onto the stack in the similar way push was doing it, right? So if you require to store your contents of flag register onto the stack, this can be used, push f and pop f, right? So when you call functions, this might be sometimes necessary. And notice that there is no gap between push and f, so it is a single command, push f and pop f. So for keeping the flag register onto the stack, or for changing the values of the flag register, the entire flag register, by taking something from the stack. So this can be done, right? Then we have this command xchg, which was also present in 8085, xchg destination comma source. So this will exchange the data which is kept at this destination and source. Now the important point about this is, destination and source both cannot be memory locations, and immediate addressing is not allowed, right? So this destination and source, I mean, you could write inside this destination bracket si, and for source you can write bracket di, where si and di points to different memory locations. But this is not possible, because if you want to transfer the data from externally interfaced memory of the microprocessor to anywhere, then microprocessor's internal register have to be involved. They cannot be bypassed ever, right? So that is why the only exception is, destination and source both cannot be memory locations, and immediate addressing is not allowed. Why is immediate addressing not allowed? Because if you write the immediate address here in place of source, if you write the immediate address here inside big brackets, then this exchange thing will not be possible. Exchange is possible at two it is possible for destination and source where there is a capability of storing data. But if there is an immediate address in your command, then in that case, where will you keep the data for that? Immediate address is for your ready reference. So that is why the immediate addresses are also not allowed into this xchg command, right? So this command was also there in 8085, and we have seen how it works. Now this is another important command, LEA register. LEA, and this register could be any of the registers, any of the 16-bit registers that you have seen in 8086, except the segment registers. So this LEA, load effective address, the full form is load effective address, and this BX and DI, we have seen in indexing, that for making double loops, we could be using this BX and DI register in some combination. So what it will do is, it will add the contents of BX and SI, it will add the contents of BX and SI, and the effective address of that will be loaded into this register, whatever register you will specify here, AX or CX or DX or whatever register. The effective address, that means the addition of BX and DI, will be stored into this register. So it only loads the effective address, load effective address. It does not load the data from that memory location. No, even you have written this in brackets DX and in brackets DI, that does not mean that data from that location will be loaded into this register. Only the effective address BX plus DI will be loaded into this register, 16-bit register. Now these next two commands are very important, and they are used in some context, but let us understand them first. LDS BX comma in brackets 3125. Now what will this do? Obviously this has got something to do with the DS, that is the data segment register, which is there in the microprocessor 8086 register stack itself. So this data segment register and BX register, these will be used in this LDS command. And what will it do? Since it is having this L here, so it will load something. Load something. So load where? Where will it load something? So it will load into combined DS and BX. So after the execution of this command, something will be loaded into the DS register, which is a 2-byte register, and something will be loaded into the BX register, which is also a 2-byte register. And where from will it be loaded? So it will be loaded from this address 3215. So inside the data segment at this offset address, you will consider four successive memory locations. So you will consider 3215, 3216, 3217, 3218. So you will consider these four memory locations, and that way you will have total 4 bytes. You will have total 4 bytes. And here you can see that DS is of 2 bytes and BS is of 2 bytes. So those 4 bytes will be stored in this DS register and BX register in this order. I mean, if you start from 3215, and this will be stored in BL. 3216 is stored in BH. 3217 is stored in DS. 3218, the content of that memory location will be stored in DS higher order byte, because in DS register we do not have DL and DH terminology. So DS lower byte and DS higher byte, right? So this is going to load 4 bytes into DS and BX register. So this is used in some specific calculations, like when if you have suppose stored the uh, location of something to be able to return to that after a function execution is done. So in that case, you can store the return addresses, or you can load the return addresses from some memory locations. So 4 bytes are used. However, this command is rarely used. If you are making advanced application, then in that case this is used. So similarly, an equivalent command for extra segment is also there. So LES BX comma 3215. So it will do the same thing. The context will be for the extra segment. So it is going to work as same as this LDS command. LES command will be working for extra segment, right? So 4 bytes of locations will be copied from the externally interfaced memory to these microprocessors, right? Then you have this command LAHF. So as the command specifies, load AH register with the content of flag register. Now the point here is the flag register is of 16 bits, and the AH register which is written here, this AH register is of only 8 bits. So load AH register with the contents of flag. So obviously you won't be able to load the complete flag. You would be able to load only 8 bits from that. So whether it will be the higher order 8 bits or the lower order 8 bits, so it will be the lower byte of the flag register is loaded into AH, right? So this lower byte of flag register is loaded into AH, and a complementary command to that would be SAHF. So whatever you have kept in this AH register, it will be copied to the lower order byte of the flag. And why are we biased towards this lower order byte of the flag, not towards the higher order byte of the flag? Because if you see the higher order byte of the flag in 8086, it mostly contains the instructions regarding interrupts and trap and machine control kind of things. So we do not need to tamper with that. However, when you make functions and you want to return to some return from that function, so most of the times the contents of parity, auxiliary, carry, etc. needs to be preserved. So this lower order byte of the flag is most of the times changed. So that is why they have given this special command. There is no such command for us higher order byte of this flag register. So lower order byte can be changed. Either you can copy it or you can change it by using SAHF command. Now the next command is very important, exlat command. It is used for implementing lookup tables. It is used for implementing lookup tables. So can somebody quickly tell me what do you mean by lookup tables? You must have read this in your data structures course. What do you mean by a lookup table? All of you, please raise your hands if you are still there. Only 32 people, 34. Okay, Nirmal Kumar, are you there? Nirmal Kumar?
Yes, sir.
Yeah, tell me what is a lookup table?
So lookup table in data structure is a hash table where we store key value pairs and
Yeah, you
we
store key value pairs. That is the definition. Okay. So you should participate. All of you should participate. When I ask questions, you should answer them. Otherwise, what's the point of having interactive classes, right? So lookup table means a table which has got a key value pair. So Nirmal has given one example that it can be used for implementing hash tables, right? So in your algorithms and data structure course, you have got hash tables where there is a usage of lookup tables. But the definition of lookup tables is this, simply this: you have got a key value pair. I mean, suppose I create a set of codes, and by those codes I mean something, right? So suppose when I say your roll number, if I say your roll number, I will mean that the candidate corresponding to that roll number is being called, right? So every one of you has got a roll number. So if in one column I put all of your roll numbers and in the second column I put all of your names, so that will be a lookup table. The key there will be your roll number and the value there will be your name, right? So it is a key value pair. So by key you mean something. So that is what we mean by a lookup table. And lookup tables are very useful. All of you can put down your hands. So lookup tables are very useful, and for facilitating that, you have got this xlat command. This xlat command is there, and this is used to implement a lookup table. And obviously, since there is a lookup table, so that lookup table will be stored somewhere in the externally interfaced memory, because the table is not bounded in terms of size. So you can have a lookup table of any size, and the internal registers are not capable enough to store big amount of data. So obviously, the lookup table will be stored in the externally interfaced memory, right? So where is it stored? How is it stored? Where are the addresses stored? That's what we need to know. So lookup table, it uses bx as the start of lookup table. So bx as the start of lookup table in data segment and al as the offset. So suppose we are dealing with the data segment. Inside the data segment in the externally interfaced memory, we have kept some lookup table. So the starting address of that lookup table will be kept in this bx register. It will be kept in this bx register, and the offset of various locations in that lookup table will be kept in al register, right? So ds register, it is already I mean, if you see this data segment, the offset register of data segment is kept in ds register inside the microprocessor, and si or di registers will be keeping the offset addresses. The base address is kept in ds register, and the offset addresses are usually kept in si or di registers. So inside that, if you want to make a lookup table, that lookup table will have its separate beginning or separate base address, which will be kept in bx register, and the offset of various elements in that lookup table will be kept in this al register, right? So let us see an example for this xlat instruction, because this is very helpful instruction in various cases. So for that, I have made this very small program. So let us try to understand this program, right? So first of all, I have simply initialized my data segment by using these two commands. Inside this AX register, I have moved a value of 5000H, which means that I am starting my data segment from physical location 50,000H, right? And after initialization of the data segment, I want to initialize the location of my lookup table. So the base address for that lookup table will be kept in bx register. So you see here 0003 is the base address of that lookup table. Can somebody tell me what will be the physical address of that lookup table?
30.
30. Is it 30 or is it something else? See, your data segment, it is beginning from, let us write everything here so that things will be clear. Data segment is beginning from 5,000, right? So this is the base address. I mean, 50,000 will be the actual physical address. Inside your data segment, I mean, let us say this is your complete data segment of 64 kilobytes. So I will just put some lines here so that things will become clear. So all border, right? So this is your data segment. The first location happens to be this 50,000 here, and here you are keeping your data. Let's say in this section you are keeping your data, right? So this is the very first location. Now inside this data segment, suppose I want to define my lookup table into this region, so let me just mark it by different color. So this is the lookup table that I want to design. So the base address of this lookup table, I am saying that is 0003. Sorry. So zeros will not be appended before something. So I will write 0.0003. So it will show it as 0003. So 10 is additionally appended. So, okay, let me just write it like this. It is 0003. So this will be 0003. Now this is the base address. So here for lookup table, if the base address is 0003, you don't have to append a 0 after it to calculate its actual physical address. Because if you see, lookup table is inside the data segment, and the beginning address of that is also a 16-bit address, right? So if you want to calculate the actual beginning address of a lookup table, it has to be this 50,000 plus 0003. So 50,003 will be the beginning address of your lookup table. Is this thing clear to everyone? Is this thing clear to everyone? Yes or no?
Yes, sir.
So the terminology base address may sound confusing sometimes. For lookup table, the base addresses are not the base addresses in the same context as it was for the data segment. For data segment, the base address was there and the actual physical address was obtained after putting up zero after this total hexadecimal number. But for a lookup table, the base address is also actually an offset address in the data segment. It is an offset address in the data segment, but it marks the starting of your lookup table. So to be able to get the actual physical address, you have to actually add this base address to the base address of the original data segment after appending a 0, right? So that's what we have done here. We have initialized this bx with 0003h, and we want to access the fifth location in the lookup table. Which will be at the offset address, which will be at the location. I mean, if you see 3 plus 5 will be 8. So it will be at the 8th location, right? So it will be at the 8th location if you see it from the beginning of the data segment, or it will be the 5th location after this 3, right? So that location we want to access. So we said that the base address of the lookup table should be kept in BX register, and inside the AL register, you should be able to keep the location which you want to access in that particular lookup table, right? So let me just emulate this code, and let us try to populate the data segment which now begins from 5000 h. Let us try to see that location, and in that 5000 data, I mean 50,000 location from where the data segment begin, I said that I will be beginning by lookup table from 50,003. So let me just try to put some values here. Let me just try to change it as 1. Let me put 2 here. Sorry. This is 1. This is 2. This is 3. This is 4. Then this is 5, 6, 7, and so on. So I'm just filling it up to 5009, and rest values of the lookup table I have assumed to be already filled. Now somebody just see the code. The code is written here, and tell me how big your lookup table can be. How big your lookup table can be. The base address of the lookup table is 0003h. The offset that you want to access is kept in your AL register. So it is 05h. So does these two things, they give you an information about how big your lookup table will be? Anyone? Please raise your hands if
Sir,
you're
can
already
you
there.
repeat your question?
The question is very simple. The question is very simple. I have created a lookup table inside my data segment. I just want to know the maximum number of locations that I can utilize inside that lookup table. Is it arbitrary or is it restricted to some number? So the answer is it is restricted to some number. I want to know that number by looking at these two things, Bx and Al, because Bx marks the beginning of the lookup table and Al marks the location which we are trying to access in that lookup table. So anyone who can guess what could be
Sir,
the size? Yes, tell me.
minimum 8 from starting.
Minimum?
8 from starting means 50,000.
No, I want to know the maximum number of locations that can be utilized in this case. See, AL, what is the size of AL? It is of 8 bits or 1 byte. Is it or is it not? The
Yes,
size
sir.
of AL happens to be 1 byte. So it will be able to take the numbers from 0 to 255. That means only that means a total of 256 numbers, right? And AL you are using as offset for this lookup table that you have created. So after 255, I mean, if you fill this AL register with FFH, what next location will be there if you again increment it by 1? It will be again 0000 with a carry equal to 1, right? So AL will decide the maximum size of your lookup table because that is the register which you are using to access different locations. So 256 maximum locations can be there in the lookup table. Is it clear or not?
Yes, sir.
So, I mean, if you again see that location number 5000H, I have already filled my lookup table starting from 5003 with numbers as 1, 2, 3, 4, 5, 6, 7, and you can fill 256 such locations, but I have filled it up to 7 only. And now we are going to, access this fifth location from the starting. So this is first location, second, third, fourth, and fifth location. So we will be accessing that particular data. So let me just run this code and let us see the changes in the registers. So we want to see the execution of this xlat instruction. So xlat instruction will copy the data at this fifth location into the into your register, right? Into the A lower register, right? So let us see it is. So the data of 6 is already there. The data of 6 is already there. So if you again see this location number 5000, base address 5000, and this is 000H. So this is the beginning of your lookup table, and if you want to go plus 5 after that, so at this 8th location you have got the data of 6 which is kept in AL register after the execution of this xlat command. So that way you will be able to access your lookup table. I mean, there is a key value pair in the lookup table, and the key value pair is there, and the values that you have kept, they are kept in these memory locations. And your AL, it will contain the keys that you have kept in that. So for various keys you have got various values here. So this is the lookup table, and inside laboratory we will see an application of this to accomplish some program, right? So this is how lookup tables are implemented in 8086, and for that this xlet command is to be used. Xlet command is to be used, and it is a part of this data transfer operation. Right? Now, there are two more important commands which we haven't seen up till now because we haven't dealt with the external peripherals. So inside 8085, when we dealt with external peripherals, we saw in and out command. Those similar in and out command will be present in 8086 also. So you can see that there is this in command AX, 85H, then there is the out command AL, 85H. So can somebody quickly tell me if these commands were used in 8085, what will they mean? Please raise your hands if you are there. All of you, please raise your hands. Okay, so let me ask this question to someone. Only 18 people, 17 people. See, what's the point of conducting live lectures if you all are sleeping? I mean, those who have not raised their hands, they are obviously not able to listen to what I am saying. So, what's the point? Okay, Tushar Gupta, are you there?
Yes, sir.
Yeah, you tell me what is the usage of this in and out command in context of 8085?
Sir, these commands are used to take input and output and
From
give out.
where? From where?
Sir, there are separate registers for these.
Separate registers. No, that's not the correct way. Utkarsh Mishra, are you there? Utkarsh Mishra absent? Satyam Abhishek, are you also not there? Should I treat you as absent? You have raised your hands. Harsh Yadav?
Present, sir.
Yeah, Harsh, tell me what is the use of in and out commands in 8085? You don't know it, Harsh? Okay,
No, sir.
Manaswini Joshi,
Yes, sir.
could you please elaborate what is in and out command in 8085, not in 8086?
Sir, when we use IO, we would be sending 8-bit address to, sir, it's like,
Okay, let me explain it. So this in and out command is used when we are using external peripherals, right? So external peripherals can be interfaced to any microprocessor in two ways, right? So they can be interfaced in two ways. So one way is you interface them in the input output mapped input output mode, or the second way is you